don't like scaring people, so it's hard to talk about this kind of stuff. The movie WALL-E gives one of my favorite allusions to the future of space debris. It shows the Earth surrounded by a shell of space trash that has accumulated over the years, and when they go to leave the planet, they have to break through it. It may not be that far off from what our future space environment looks like. To get an idea of our current space environment, imagine this ball is our planet, and this sand is space debris. At first glance, you might think, yeah, there's a lot of stuff, but it's small and fairly spread out. And you'd be right in some ways. Full scale, the objects are usually further apart than mountaintops, so the chance of any two colliding at a given moment is pretty small. But they're all moving around in orbit, so as time passes, the chances build up with every moment of every day of every year. Many astronomical events are considered rare, but there are many astronomical events. In that sense, it can be quite common to have a rare event.
The 2009 Cosmos-Iridium collision was pretty awakening. Less than 500 miles above the Earth, two satellites bumped into each other at over 15,000 miles per hour. The debris field from accidents like theirs spread out like a shotgun blast, threatening other spacecraft with the same fate. This cascading effect was first predicted by Donald Kessler in 1978 and is rightfully called the Kessler syndrome. We are already past the tipping point for the problem to fix itself. The longer we wait, the worse it becomes.
When we think of accidents, we usually think of two cars kind of banged up a bit. And with the exception of a little glass or maybe some taillight plastic, they both leave the scene with most of their original parts. But accidents in orbit, they happen on a completely different level. And the reason for this is the amount of energy transferred. And I'm on my way to show you exactly what can happen if you transfer enough energy to a system. The explosion transferred enough energy to the building to make it crumble to pieces. Space debris is traveling so fast that the kinetic energy transfer to impact is enough to do the same. Loosely speaking, a piece of space debris can be categorized as big, little, or tiny. Old satellites and rocket stages are big. If they break up, they have enough material to scatter thousands of little pieces. These little pieces are harder to track and still very dangerous. Tiny pieces are too small for us to track, but they're not nearly as dangerous. The potential clutter that big objects can create makes removing them most important for the long-term goal of cleaning up space. But every time a big object breaks up, there's a heightened short-term need to clean up the pieces before they continue the chain reaction. But now we get that there's a problem, so let's fix it, right? The first idea that usually pops into people's heads is to launch a satellite to go collect each object individually, and then send the whole cluster to burn up in the atmosphere. Let's call this the standard mission. The standard mission doesn't work. The fact of the matter is that space debris is very scattered, and it takes a lot of fuel for a satellite to transfer orbits and rendezvous with each object. The standard mission would only be able to collect a few objects before its tanks ran dry. There's been a lot of creative and advanced ideas proposed, but So far, none of them have been proven feasible. More aggressive plans are often viewed as potential weapons against functioning satellites, so they can be impractical for political reasons. Passive techniques can also be threatening. Functioning satellites are just as likely to be snared as debris. Still, others depend on technology that has not yet been developed. By definition, they're not ready to start fixing the problem now. The best solution for taking action now is to somehow make the reliable and assertive standard mission more fuel efficient. TAMU Sweeper is a mission structure doing just that. In the standard mission, we burn fuel to match the debris velocity. We capture it softly, then burn more fuel to transfer to the next debris, then match its velocity, and so on. Now what if we had a satellite designed to withstand collisions? We would not need to waste fuel matching the debris velocity. Not only that, the collision would change our motion, a free boost that can help us get to the next debris instead of burning fuel. Take this one step further. What if we ejected the debris after capturing it? This would give another boost that can be used in place of fuel. It also saves future fuel by shedding the debris mass. The ejected debris would be set on a path to fall back to Earth, removing it as a threat. This is the basic idea behind TAMU Sweeper. It is efficient and receives 2 free boosts, or impulses, for every object that it interacts with.
Left to their own devices, these impulses are not necessarily helpful. They are just free. The key to making this successful lies in a clever optimization process that looks at all possible capture and ejection combinations and determine which is the most efficient and effective at debris removal.
The last piece of the puzzle is the satellite itself. It has to be durable, precise, and efficient. And Sling-Sat may be just the one for the job. The basic idea behind Sling-Sat is to have a spin-stabilized satellite that collects debris at the ends of adjustable arms. Adjusting the length of these arms controls how fast it spins, which also determines the ejection speed. Setting the ejection angle is just a matter of timing when to let go.
TAMU Sweeper and the Sling-Sat actually use the vastness of the space debris problem as part of his own solution. This idea is somewhat new, but simulations are already posting some promising figures, the kind that may finally make space debris removal practical.